Chapter number 5, which is laws of motion. We are discussing laws of motion. In the previous discussions, we have talked about the motion of a particle in a space, and that too we talked it in the quantitative basis. Then we talked about the concept of velocity and non-uniform motion, and then we talked about the acceleration. But one question we didn't ask, that what is governing the motion of bodies? In this discussion, we are going to discuss this only. Let us see what our experience says. When the football is at rest, why is it at rest? When someone kicks it, why does it move? When we throw a stone upwards, what is the thrust or force or push you give so that it reaches upward? A breeze may cause the tree to swing, and even the strong wind can move heavy objects. The boat which is moving in the river, if you're rowing it. So there is some external agency in all these scenarios that is providing some force. So there is some or the other force which is making this body to move. This external force is also required to stop something. Means this ball which somebody has kicked, football, then you can just stop it and it will come into, you can say, rest. The external agency of force in all these scenarios, it can be your hand, it can be wind, it can be stream, and these are all in the contact with the object, but this is not necessary. Take a scenario, you are dropping a stone from, say, a building. Now there is a gravitational pull here. So this is not having any contact with anyone or any other agency, but it is having a contact or some kind of pull with earth. A bar magnet can attract iron nail from a distance. So what this shows is that the external agencies, gravitational, it can be magnetic forces, this also exert force on a body, and that is at a distance. See, it can be, say, 100 meter, 200 meter. So the force is required to put a stationary body either in motion or to stop it, means to stop it. And there must be some external agency which is providing this force, and as discussed here, the external agency may or may not be in contact with the body. But what happens if a moving body which is moving uniformly, that is, say, a skater, he is moving with a constant speed on a horizontal ice slab? Do we require any external force to keep a body in this uniform motion? We have Aristotle fallacy. Now Aristotle gave his ideas, his view. And why this is called fallacy? Because there is some flaw in his argument. The question about what is the force or how the motion of the body is governed, it was somewhat discussed by Aristotle, and then Galileo came in the 17th century, and he gave you can say the flaws he cleared, and then Newton came, which gave rise to Newtonian mechanics. Basically, what Galileo has thought, or what he has posed in front of us in the 17th century, this is the foundation of Newtonian mechanics. So what happened? Aristotle, he was a great thinker. He thought that if a body is moving, something external is required to keep it moving. He gave certain, reasons also. He said that arrow shot from a bow, it keeps flying since the air behind the arrow keeps pushing it. And people that time, they might have believed, and most of his ideas, Aristotelian ideas on motion, they are proven wrong today. But because he started, we need to understand what he said. The Aristotle law is like this: an external force is required to keep a body in a motion. And what is the flaw? Anyone of common experience or common intellect will go with what Aristotle has said. Even a small child who is playing with simple, say, non-electronic toy car on a floor, he knows that he has to either pull it or push it, say, constantly drag the string toy car with certain force in order to keep it going. Now, if he has a string and he releases the string, it will come to rest. This is common to all terrestrial motion also. We understand that there are certain external forces. This seems to be needed to keep bodies in motion. And all bodies, they eventually come to rest. So what is the flaw? See, the moving toy car come to rest because of the external force of friction on the car by the floor, which is opposing its motion. So in order to counter this force, the boy or the child has to apply certain external force on the car in the direction of motion. When the car is in uniform motion, there is no external force acting on it. The force which child has exerted, or he has pushed, the friction force and this force will get cancelled out. So if there were no friction, the child would not require to apply any force to keep the toy car in uniform motion. So we have opposing force like friction in solid, viscous force in liquids or fluids that are present in natural world. And that is why we know that external forces are required to overcome this frictional force in order to have a uniform motion. So this is the Aristotle fallacy. He coded this practical experience in the form of just basic argument. And if you want really to have forces and motion and the nature and the laws, then we have to imagine a world in which uniform motion is possible with no friction force opposing. And this is what Galileo did. The law of inertia. Galileo, he studied the motion of the objects in the inclined plane. He saw that the ball which is moving up, which is coming down, or which is in the horizontal position, these all scenario he took. And he finally concluded that an object moving on a frictionless horizontal plane must neither have an acceleration nor retardation. Acceleration means increasing the speed, retardation means decreasing the speed. So when it has no acceleration, that means it is moving with the constant velocity. There is another experiment which Galileo did, and this also strengthened the idea which he discussed here. And this was double inclined plane. So a ball was released from the rest on one of the planes, rolling down, and climbs up here. If the planes are smooth, the initial height and final height, they are nearly same. So what is the ideal situation? When friction is absent, the final height has to be equal to the initial height. Now if the slope of this second plane is decreased, And again this experiment is repeated. It is done again. The ball is going to reach at the same height, but it has to travel a longer distance here. And in the limiting case, the slope of this second plane is made 0. The ball would travel an infinite distance if it is dropped from here. Or you can say the motion will never stop. But we know this will not happen. This is not an idealized situation. In ideal situation, it should not stop. So this is the experiment. These two experiments. The law of inertia was inferred by Galileo from these observation of motion of a ball on especially these double inclined plane. We see that ball always come to a rest after some time because there is opposing force which is friction. We cannot totally eliminate it. It will be there. But you will see that with no friction, the ball would continue to move with a constant velocity on a horizontal plane, if in case friction would not be there. So Galileo now arrived at new insight on motion that had eluded Aristotle and those who believed in Aristotle. The state of rest and the state of uniform linear motion, that is motion with the constant velocity, they are equivalent. Again, the state of rest means if the body is settled down, not moving anywhere, and the state of linear motion, if it is moving like this, they are equivalent because there is no net force acting on it. Net force means a body may be subjected to certain force like this one, and the final force we have to find out. So that is the net force. So it would be incorrect to assume that net force is needed to keep a body in uniform motion. In order to maintain a body in uniform motion, we need to apply an external force, and that is to encounter, you can say, counter the frictional force. So these two forces sum up to 0 net external force. So let us summarize. If the net external force, that is this one, is 0, the body at rest continues to remain at rest, and a body which is in motion will continue to move with a uniform velocity. And this property of body is known as inertia. This is known as inertia. Inertia is simply meaning any resistance or the resistance to any change. That means the body does not change its state of rest like this or uniform motion unless it is compelled to do so or some external force is applied to change that state. Newton's first law of motion. Galileo, the ideas he gave, actually Aristotle started all, and then Galileo gave the flaw in Aristotle and he corrected the concept. After that, new mechanics was developed, and this was accomplished single-handedly by Isaac Newton, one of the greatest scientists of all times. Newton started, or he took Galileo's ideas as the base, and then he laid the foundation of mechanics in terms of 3 laws, which we know by his name. So Galileo's law of inertia was the starting point, which was he formulated in terms of first law of motion. Every body continued to be in the state of rest in a straight line or uniform motion in a straight line unless it is compelled by some other or external force not to do so. So the state of rest or uniform linear motion, they both imply 0 acceleration. Acceleration is 0 while the body is at rest or in uniform velocity. How can we express it again? If the net external force on a body is 0, its acceleration has to be 0. We'll see later that in the second law of motion, F is equal to ma. We'll learn about this. So F equal to m into a. If the acceleration is 0, force is 0. So acceleration can be non-zero only if there is a net external force on the body, right? This can only be non-zero when you have some force here. The net external force in the body, if it is 0, as we said, because of this discussion, the body is either at rest or it is moving in uniform motion. A spaceship out in interstellar space, which is far from all other objects and with all its rockets turned off, it has no net external force acting on it, that is 0 force acting on it. So the acceleration, according to the first law, it has to be 0. If it is in motion, it has to move with uniform velocity. So where does this force comes? That the object is, say, accelerated or unaccelerated. You can say if it is unaccelerated, that means it is in rest or uniform linear motion. What we can infer is that by first law, that the net external force on an object must be 0. But gravity is everywhere. If you take any terrestrial phenomena, every object experiences some gravitational force which is due to the earth. And the objects in motion, they generally experience the friction, the viscous drag, so many things. So the net force which is acting is very important. We'll learn about that, how those forces cancel up, how those forces they get added up. Just consider a book which is lying on the table. Now there is a force of gravitation which is acting downward, which is W, weight. There is a normal force opposite to it, and this R is self-adjusting force. These forces are opposite to each other. That is why, and what is happening? This book is at rest. So what we can conclude by the first law, that the magnitude of R has to be equal to W, because this is at rest. So all the net force which is acting on this body should be 0. So there is only two forces which we can conceive here. One is weight, one is some reaction force. So R has to be equal to W, and they cancels out. And since they cancel out, the body remains at rest. But is this reasoning correct? The correct discussion should be, since the book is observed to be at rest, there is no net external force on it, or the net external force on it must be 0, 0. So R minus W equal to 0. This should be the proper reasoning. That means the force, this R, has to be equal and opposite to this weight. Let us take one more example, that is a motion of a car which is starting from rest. It is starting with initial velocity 0. That is picking up speed and then moving on a straight road, and now it has uniform speed. When the car was at rest, that is, it was stationary, there was no net force, but during pickup, you push the acceleration is being pushed by you. Okay, and there would be some external force. That is why it has accelerated, and there is no external force here because the acceleration is coming from the engine. So the acceleration of the car cannot be accounted for by any internal force. But it is true. It is surprising, but it is true. We need to understand only the conceivable external force along the road is the friction force which is acting between the tires and the road. This is the friction force which is being acted upon. So when the car is moving with constant velocity, there will be no net external force. And the inertia, body will continue in rest, body will continue in moving the state. When we are standing stationary in the, say, stationary bus, and the driver starts the bus suddenly, what will happen? We will get thrown backward with a jerk. Why? Because our feet, see, we are sitting like this. Our feet are in touch with the floor. So if there were no friction, we would remain where we are, while the floor of the bus would simply slip forward under our feet, and the back of the bus would hit us. But what happens? Fortunately, there is some friction between our feet and the floor. So if the start is very fast, if it is not too sudden, you can say the acceleration is moderate. The friction force would be enough to accelerate our feet along this bus. But our body is not a rigid body, it's flexible, it is deformable. So it allows some relative displacement between different parts. We can move our parts. So which means that while our feet go with the bus, the rest of the body remain where it is due to inertia. So relative to the bus, therefore we are thrown backward, and as soon as this happens, our muscular force, body forces, they start acting upon, and they play to move the body along the bus. And this same scenario will happen when the bus will suddenly stop. If it suddenly stops, our feet stop due to the friction, which does not allow relative motion between the feet and the floor of the bus. But the rest of the body continues to move forward due to inertia. That is why we are thrown forward. But we have restoring muscle forces. This will come into play and bring our body to rest. Let us take a question. An astronaut accidentally gets separated out of his small spaceship accelerating in interstellar space at a constant rate of 100 meters per second square. What is the acceleration of the astronaut the instant after he is outside the spaceship? We have to assume that there are no nearby stars that are going to exert gravitational forces on him. And since it is being said that there are no nearby stars to exert gravitational force on him, and this small spaceship exerts very little or negligible gravitational force or pull, the net force acting on the astronaut when he comes out of the spaceship is zero. And we know by the first law of motion, the acceleration has to be zero. Newton's second law of motion. The first law of motion, it deals with the external force, that is no external force on a body. If there is no external force on a body, or the external force on a body is zero, then the body will remain at rest, or it will remain in uniform motion, uniform velocity. The second law of motion, it refers to general situation when there is net external force acting on the body. That is, it is relating the net external force to the acceleration of the body. Momentum. What is momentum? P, represented by P of a body. This is simply defined as the product of mass and velocity. So P will be equal to mass into velocity. Momentum is clearly a vector quantity because velocity is a vector quantity. we have certain experiences that will indicate the importance of quantity for considering the effect of force on motion. If we have a lightweight vehicle and a heavyweight vehicle which is parked on the road, now which of the body would need greater force to move? See, and even to move, to start, and to stop. In both the cases, which body will require more work, you can say. Heavy body, we need to work a lot with heavy body, and even to stop it, we need to work very hard. If two stones, one is light and other is heavy, they are dropped from the same height from a building, say they are two stones like this, and which one is easier to catch and which is going to affect, so if you are catching, then which is going to hurt you more? Speed is also a very important parameter when we consider all this. Speed, when the bullet is fired by the gun and it pierces human tissues, it causes casualty. But if the same bullet is fired with some, say, moderate speed, it may not cause that much damage. So for a given mass, if the speed is greater, the opposing force which is required to stop this body will be larger. So if we take mass and velocity, the product of mass and velocity, we know by now that it is called as momentum. And this is a very relevant thing which comes into play in terms of motion. So greater the change in the momentum for a given time, greater is the force applied. See how this momentum is related to the force. Just take an example. A seasoned cricketer will not just catch ball right here. He will catch the ball and he will take it backward. Why? Because there is a momentum, there is a mass in this body, and with a velocity it comes. So the rate of change of momentum, he wants to make it less. So force not only depends on the change in the momentum, but also how fast the change is brought about it. As we see here, the seasoned cricketer, he draws in his hands during a catch, and he pull it backward, allowing greater time for the ball to stop, and that is why he requires smaller force. So the rate of change of momentum becomes a very important property here, or you can say momentum becomes a very important property as far as force is concerned. So mass and velocity, as we say, it is momentum. This is the basic to the effect of force on motion. If we have fixed force which is applied for a certain interval of time on two bodies of different mass which are initially at rest, the lighter body will pick up a greater speed than the heavier body. But at the end of the time interval, the observation will show that each body acquires the same momentum. So what this says is, the same force for the same time, the same force for the same time causes the same change in momentum for different bodies. And this is very crucial when we are discussing the second law of motion. So in all these observations, because momentum has velocity, the vector character or vector property comes into play. The momentum and change in momentum, they both have same direction. But this is not always the case. Say you have a string and you have a stone at an end of the string, and then you are moving it. Now here the direction will change. So the force is needed to cause this change in momentum vector. See, the force is provided by our hand through the string, and this experience will suggest that our hand need to exert a greater force if the stone is rotated at a greater speed or in a circle, so say it's in a smaller circle. So this corresponds to greater acceleration, will give rise to greater acceleration, or you can say the rate of change of momentum vector. This is suggesting that greater the rate of change of momentum vector, the greater is the force applied. So force is somewhere directly connected to the rate of change of momentum. So these qualitative observations lead us to the second law of motion, and which is expressed by Newton like this. The rate of change of momentum of a body is directly proportional to the applied force, and this takes place in the direction in which the force is acting. Say you have a force F, this is acting for delta t time. So the velocity of a body, say of mass m, it changes from v to delta v. In delta t time, the velocity changes delta v. So what will be the initial momentum? It will be simply p equal to mv. What will be the final momentum? Delta p will be equal to m delta v. And according to the second law, the force is directly proportional to the rate of change of momentum. So F is directly proportional to rate of change of momentum. So this is proportionality. Let us remove this, put a k here. So this k is the constant of proportionality. When we take the delta t, that is delta t limit tends to 0, when the time is very less, we make it. This delta p by delta t will eventually become the derivative or differential coefficient of p, which we represent by dp by dt. So now this f becomes k into dp by dt, and we know that dp by dt, p is what? M into v. Let us put p equal to mv here. Mass is constant, so take it out. This dv by dt is what? This is acceleration. So finally, f becomes k into m into a. This shows that the force is proportional to the product of mass and acceleration. This is the law which we are discussing. So the unit of force, what will just take a liberty that this k will choose as 1. So F is equal to ma. Now mass and velocity or acceleration. So the SI unit of force is 1, that will cause an acceleration of 1 meter per second square in a body of mass which is 1 kg. This unit of force is known as Newton. 1 Newton equal to 1 kg meter per second square. So there are certain points. If F equal to ma, F equal to 0 implies acceleration equal to 0. This is obviously consistent with the first law. If there is no acceleration, body will be at rest or body will be in constant velocity. The second law of motion, this is a vector law. So it is equivalent to the 3 equation in fx direction, fy means ax, x direction, y direction and z direction. So fx will be dpx by dt, that is max. Fy will be dpy by dt in y direction. So it will be may, and this will be dpz by dt for fz. This will be m into az. So this means that if a force is not parallel to a velocity of the body, this velocity is like this, force is somewhat like this, then it will make certain angle, and the component we have to see. We have to take the component, this component of velocity, which is horizontal, will be in the direction of motion, but the vertical will not change. We'll talk about the projectile motion, where we see that what is changing is the horizontal component only changes, vertical will remain like that. And this second law of motion is applicable to single point particle. The F and A, the law of motion applies to rigid body, or you can say a system, a whole system. This F, it refers when to total external force on the body or a system, and A refers to the acceleration of the system as a whole. That means this can be a simple body, and this is a whole system. You have a train, you have all those things which are happening here. So any internal force is not included. Please understand, no internal forces are included. The second law of motion is local relation, which means that force at any point is local at some instant, which is related to the acceleration at that instant only, not by the history of motion. That is, if you throw a stone out of this running, say, moving cart or train, then once it is out of this system, or you can say out of this train, the force and acceleration will not depend on this anymore. So it will be local. Here only we'll find out. The bullet of mass 0.04 kg moving with a speed of 90 meter per second enters a heavy wooden block and is stopped after a distance of 60 centimeter. What is the average resistive force exerted by the block on the bullet? So the retardation acceleration, we know that you can use easily v square equal to u square plus 2as here. Acceleration, because retardation is there, so it will come in negative. The distance is also given 60, so we have to divide it by 100, so we get 0.6. And mass is also there, but the initial velocity is 90, the final velocity will be 0. So when we put all these values here, acceleration is this much, minus 6750 meter per second square. And then you can easily find out the force, because the question is about force. Now this is the acceleration and the mass is 0.04. So mass into acceleration is the F, right? Force. So this is the resistive force, and basically it's a retardation. No, the bullet is coming, so it has to stop. This is the question is all about. The motion of a particle of mass m is described like this. Find the force acting on the particle. So we have y equal to ut plus half gt square. Let us take the differential. So this dy by dt will be equal to d derivative of ut and half gt square. So we'll derivate in terms of t. So v will be dy by dt. This t will go. This t square will become 2t. So this will be v. Again, let us differentiate it again, because acceleration is dv by dt. So let us take a derivative of this one. This will go. This g will remain like this and t will go. So acceleration is actually equal to gravity. So what will be force? Force is mass into acceleration. And in this case, a becomes equal to g. So this will be g. F equal to ma or mg. This is the, and this equation describes the motion of a particle under the action of or acceleration of gravity. Impulse. When you are hitting a cricket ball, or say hitting a football which is moving, so the change in momentum, or you can say the force, is acting for very short duration, which is changing the momentum of the body, velocity of the body, because mass remains constant. The scenario here is that for a very small duration, a heavy force is applied. So we come to another variable or property in motion, which is the product of force into time. Force applied for certain time, and this time is very less, and which is causing the change in the momentum, because velocity is being changed, so momentum is being changed. And this is the measurable quantity, and this we call it as impulse. So impulse will be simply force into time, which is equal to the change in momentum, which is causing the change in momentum, and which is we can say a large force acting for a very short span of time. It produces a finite change in momentum, and this is called as impulsive force. This impulsive force, and traditionally they were put in ordinary forces, but as we know, Newtonian mechanics, they have no such distinction. Impulsive force are like any other force. The only thing is they are very large and they act for a very short time. Let us take an example. A batsman hits back a ball straight in the direction of the bowler without changing the initial speed, that it remains 12. If the mass of the body is 0.15 kg, we have to determine the impulse imparted to the ball. Now the initial momentum was m1 v1. The final is m2 v2. We know that the mass remains the same, so it will be simply, let us take mass here, mv1 minus v2. Okay, so mass is, we are finding the change in momentum. So this mass is 0.15, 12, ball is coming this side, now ball is going this side. So one will be 12, other will be minus 12. So 12 minus of minus 12, that is 12 plus 12, and that is multiplied by 0.15. So 24 into 0.15, this will give you 3.6 Newton second in the direction from the batsman, because batsman has hit this ball in the direction of the bowler. So these were few points we have discussed in the laws of motion, and we'll be taking few more. Till then, thank you so much and take care of yourself.